Right. So this is where actually I'm supposed to start with, but the morning lecture I gave just to excite you about the subject of geotechnical engineering. So in this lecture, we kind of look at um, traditional static pile foundation design. Basically, design how do you design a pile for under static loads and also dynamic loads. Okay, and I'm going to follow what is the more recent ways of designing doing the static pile design. These are, I don't know whether these are the methods you will use in India or not, but I think Professor Agnihotri is going to go through the static pile design again. So in a way that is relevant to you directly. Okay, so just bear with me. But this is an interesting way to design piles. So let's start by looking at different types of piles. Not all piles are not the same. You can have a very soft clay and say rock underneath, in which case I can have my pile going through and ending in the rock. So if this soil is very soft, it's not going to offer me much skin friction. So more or less, all the load you apply is carried as the end bearing. Uh, on the other hand, if I have a very thick deposit of clay and there is no rock below, like in and around the coastal parts of my hometown, then you can only have friction pile. So you have to carry the load in skin friction or sharp friction. So these both are load bearing piles. Sometimes you also use piles just to compact the soil. So you put lots of piles into the ground, and as you drive them, the sand or the soil gets squeezed in and you densify the soil. These are called compaction piles. Um, if you have a pile cap and piles like this supporting, say, a building, and you apply a lateral load, then you expect the loads, apart from the vertical load carrying, when you apply the lateral load, these piles will go into compression and tension, and therefore they need to, here you can see, this pile, if that load is applied that way, that will push down and this will pull out. So in extreme cases, you can imagine these will be they can be pulled out of the ground as it oscillates back and forth. You can also have offshore situations where they're purely designed as tension piles. So you have some floating structure, you anchor it onto the pile, and it will be effectively holding the all the loading that pile will ever see in its life is in tension. Okay. Right. How do we do static design of piles? Basically, the piles are there to transfer vertical load into the soil. And even today, they're probably one of the parts of geotechnical engineering, if not the whole civil engineering, where you design them with very large factors of safety. Usually, you must be quite brave to design a pile which is less than factor of safety of 2 or 2.5 even. Why is that? Why are we so unsure about piles? I mean, if you are constructing an embankment, you can go factor of safety of 1.3, right? For other shallow foundations, maybe 1.5. When it comes to piles, generally people are very, very conservative. And you want to think, why is that? And that also means that you can save quite a lot of money if you can actually understand how these piles work and you can design better. So we'll come to that later. But basically, the axial capacity of the pile has two components. So the ultimate capacity is made out of the base capacity and shaft capacity. Now, how do we estimate these? So base capacity you can estimate by simply using the area times the vertical stress times some kind of a bearing capacity factor. These were done by Berzinet in 61, and where depending on angle of shearing resistance, you get the factors. So if I pick 30, it's about 30. So NQ will be 29. And you multiply that, you'll get the base capacity. What about shaft capacity? Now, the shaft capacity, you can imagine that if I can estimate the shear stress acting on the pile all the way around, and if I integrate that along the length of the pile, I should get my shaft capacity. So, you can use this type of equation where you are calculating the shear stress along the skin of the pile or the pile soil interface. You take the vertical stress, multiply that with a factor Ks, and then multiply with this friction angle. This is kind of very interesting. Why are we doing this? I don't know if you thought about this or not. So if I want the frictional resistance here, what I'm doing is at any elevation, I'm going to take the vertical stress which is acting down. I'm multiplying that with a factor Ks to turn it into a horizontal stress. So Ks is some form of earth pressure coefficient. So to convert the vertical effective stress into horizontal effective stress. That's fine. So that gives me this bit, right? Then I'm multiplying that with the friction the coefficient to turn it again vertical, which is my opposition to the settlement of the pile. So we start this way, convert that into horizontal stress and convert back into vertical shear stress. And once you got that for a elevation, I need to multiply that with that area there and integrate from base to the top. And that's what we are doing here. So at any elevation, you calculate K as sigma dash V tan delta CV, and then to get the shaft capacity, you basically multiply by the perimeter 2 pi r, integrate along the length of the pile. Sorry? Because you're pushing the pile in. Okay, so let's just look at some values. Yeah, delta CV, steel 20 degrees, concrete maybe 0.75 or 5 dash. There are many similar equations. I just picked a set. This is why I'm saying different countries do this differently. Wood maybe 0.66. So this is kind of material dependent, and it should be because steel piles and concrete piles have different surface roughness. So it makes sense that these should be different. Now, the next thing is the relative density of the soil and how Ks changes based on that. So, you can have for a low relative density 0.5, high relative density 1, and if it is concrete, if it is high relative density, you can get Ks values of more than 1. That's what you're asking, right? Now, if I drive the pile in and if the soil is getting pushed out, I'm mobilizing more like passive pressure, right? So my horizontal stress goes up because my pile is being driven and pushing my soil, and a part of that will be left out as a residual stress, and that's why you can have Ks values of bigger than what you normally expect. So here what we are saying is normally Kp is about 3 and it's not quite 3 here. And in this case where the wood can actually absorb water and swell, you can get even bigger horizontal stress. No, these are all just for vertically loaded piles. I'm only talking about that for now. Okay. But initiation will be the same whether it's compression or tension. Only thing it will change is if I'm going to pull out, then the cavity will collapse and then my earth pressure will collapse. That is at the failure state. Okay, so that is like traditional design of piles. But what is getting more popular is this CPT based design of piles. So suppose I got some soil strata like this, where I got fine sand, some interbed fine sand and silt sand, fine silty sand, grey silt and so on. Typical ones. So you can do SPT or CPT, and then from that you can actually get the relative density. These are all correlations from Paul Main and other people like that. If you have one of these, you can convert them into others. How well, don't ask me, but there are cookbook recipes. It's like making jalebi. I have my SPT data, then I can convert that into stock market variations somehow. There are some correlation somewhere. How reasonable it is there some theory behind it? God knows. So let's assume that there is a recipe and they will convert the SPT blow count into relative density and friction angle. In Europe, generally, we don't like SPT so much. We prefer CPT. Offshore, always CPT. Very rarely you can do SPT anyhow. So, say I got the CPT sounding like this, where I got my QC, which is the cone resistance corrected by some method or the other, and I got this, says, solid black line as a mean. So, if I push the cone several times, I'll get many of these, and I can take a mean, and let's say that is my black line. Now, the people started thinking back in 1980s and 90s, why are we designing piles using all these arbitrary Berzhotov method and so on if we have CPT data? What is CPT? CPT is just a rod, narrow rod, which you are pushing into the ground. And we are monitoring what's going on at the pile tip resistance, cone tip resistance, and also shaft sleeve resistance and other pore pressures and so on. So we actually got, the soil is trying to tell us, if you push an object into me, this is what I'm going to do. So why don't we use that to design a pile which is nothing but an enlarged version of the cone? So there should be a really nice correlation between CPT and SPT. That is the theory behind these methods. And these are getting quite popular. So, if I have, so this is a typical CPT truck. I believe Aniruddhan or somebody in Chennai has a truck like this, and there are a few others who can buy them, and clearly there are not enough of them. That's why we are still struggling with SPTs. But you use the truck as your reaction, and you push the rod in between. So you can see your the whole weight of the truck is your reaction load, and you push the rod inside, and you get your QC values directly from that. So, if my pile was to be a board pile, that is, if I'm going to make a hole in the ground, drop the reinforcement and pour concrete, then I can link my QC that I get from my CPT to the pressure I'm going to get or the resistance I'm going to get for the pile, end bearing of the pile. So QB over QC is a ratio that's approximately equal to the displacement I'm going to get at the base of the pile normalized with the pile diameter. Same here, plus 0.5 QC over EB. EB is the Young's modulus of the material. If it is a concrete, then you use the Young's modulus of the concrete there. So this is like a nice correlated link to the CPT. So if I have QC, I can basically get what QB is based on that for different diameter piles. If it was a driven pile, same idea, but now it will, you use this equation, and obviously this will be a lot bigger than for board piles. Board piles at the start of their life has very small vertical stiffness because they need to displace some amount to mobilize the full base capacity and shaft capacity. Whereas a driven pile, you already driven it to the soil underneath should have failed for it to arrive there. So you will start with much higher capacity. And you use this equation where again this is the normalized displacement at the pile base to diameter plus the half of that, and yeah, the only difference is the in the top you have this QB naught, which is the residual pressure. At the bottom you have QC, which is the cone resistance at different elevations. So we can get a continuous variation of the shaft of the bearing capacity with depth using this equation. Typically, you don't actually measure that. You take the ratio of the residual pressure to cone resistance as about 0.3 to 0.7 seem to fit reasonably well. So that is one way of doing it. There were these people, Richard Jardine and Fiona Chow, came up with a slightly better and elegant way of doing the same thing, and in fact, it's much easier to use. So this ratio of QB and QC, now what they are linked to is this equation where D is the pile diameter and D cone is the cone diameter. So I only need two. The diameter of the pile I want normalized by the diameter of the cone, which is normally maybe 1.5 inches thick rod. That's the cone rod, right? And this is a natural logarithm or Lund function, we call it. And this would be greater than or equal to 0.13 is the equation. So if you plot this for different pile diameters between 0 to 1.5, you can see this will tend to about 0.13, as I said. If it is any lower than 0.13, you make it 0.13. But say for a 0.5 meter diameter pile, I would get QB or QC of something like 0.38 or 0.35. Easy. So I only need to know QC, then I can work out my base capacity. And here what they're assuming is internally that as I'm pushing my pile or the cone in, the soil around is undergoing cavity expansion, and that expansion ratio is like a Lund function or a logarithmic function. Randolph later on has come up with, that is the earliest one. Then they also modified this to came up with this for driven piles to work out tau s as well. So the previous one gives base capacity, easy. This one gives you the skin friction or the shear stress along the skin, and so here you have QC over 45 and the vertical stress normalized to atmospheric pressure to 0.13 d over h to the point. I never like these kind of these basically means somebody fitted a curve. That's what these 0.13 and 0.38 are. This is the residual thing, that whole thing multiplied by tan delta CV. Tan delta CV makes sense because that's just your mu or the coefficient of friction. So that is all fine. This delta sigma dash RD is the stress increase due to dilation. You asked earlier, how come I can get my K greater than 1? This is the one that is creating. So as I am pushing the pile in or driving the pile in, the soil is expanding radially. That makes the soil to dilate. And this basically is trying to work out that stress increase due to the dilation. Okay. So that they add here and work out tau s. And then as before, once you got tau s at one depth, you integrate along the length of the pile to get the tau s. Shears. Mark Randolph actually modified this, and this is in his Rankine lecture in when did he do? 2005 or 6. It's based on his previous paper, and this tau s, what Mark says is it's not a Lund function, logarithmic function for the expansion. It should be a negative exponential function. So in a log function decays quite slowly, an exponential function decays much faster. So he, based on his experience, said, as I move away from the face of the pile, my cavity expansion pressure or the stress will decay much faster than the logarithmic function will give you. That's all the difference. It's just maths. So how do we estimate this based on this exponential function? So you take the minimum earth pressure plus difference between maximum earth pressure minus minimum earth pressure. So basically Kp minus Ka, if you like, times e to the power of minus mu h over d, where d is the pile diameter, mu is the coefficient of friction, and the rest are all known. So effectively we can recalculate tau s based on this equation which is much more reliable, and he has a lot of data to show this actually works better than the other one. So you can actually take this Kmax is taken proportional to the cone resistance QC. Basically, you need to know how much of your passive earth pressure are you mobilizing. And what he is saying is you can take that about 1 to 2% of QC over sigma dashed V. All these are in the paper. So this is not what I wanted to, as I said, you should not worry too much about the equations. It's basically you need to know why, what is the basis behind it. So this one is saying there's an exponential decrease of my horizontal stress as I move away from my pile soil interface, whereas the previous one is saying there's a logarithmic decrease. Okay, so that's all. What that we have covered so far should let you design a pile for a given load easily, whether it's board pile or friction or driven pile. That's how I would, in a typical Cambridge style, we say, yeah, we covered pile foundation design. Go away and do it. Now, obviously, here you have many more. I'm sure there are IS codes. I don't know, IS 18, 15, yeah. So there are IS codes which you have to follow, and they'll follow one method or the other. For us, it is more important that you understand where these equations are coming from. That's why I chosen the latest one from Randolph's Rankin lecture and showed you how you can use that in design. Now, IS code may or may not allow that, but then it's IS code's problem, not my problem. Okay. Right. Now I want to, we want to actually move away from that and look at the dynamic design of considerations for piles. So all we have done so far is static. First thing about piles and dynamic loads is there are two types of loads a pile will attract. One is called inertial loading and the other one is called kinematic loading. So what I'm going to do is to explain what these are, how we have methods to evaluate it at the moment, and also I'll show you whether they're any good or not. So again, the idea is there are equations, there are ways to calculate, but then you need to go and check whether what you're doing is right or not. And that's where research is important. We are not doing this for fun. Okay. First thing is inertial loading. What is it? I got piles supporting my building. The earthquake comes, it shakes the ground, the piles, and the building. Now, the building has quite a lot of mass sitting on the top, right? So, if I try to accelerate it, that is going to apply big loads onto my top of the pile. Yeah? So, for now, let us call that is the inertial load. So, the piles are the ones which are holding the building and trying to move back and forth, and the building says, no, I don't want to go, I'm heavy. So, that is why it's called inertia. It doesn't want to move. The piles want to go, the building doesn't want to go. Therefore, the building applies to the piles at the top this inertial load. So, the first thing is, if you don't design properly, all the pile heads will break and the building will break free. That's one possibility. The other one is kinematic loading. So, kinematic loading is the piles are buried in the soil and the soil is wanting to go left and right during shaking. So, it wants to take the pile to ride with it, right? But pile has its own stiffness, soil has different stiffness to the pile. Pile is made out of concrete, soil is made out of soil. So, clearly they don't have the same stiffness. So, because of this difference in stiffness, the pile will move less and the soil will move a lot more because soil is typically softer than concrete pile. So, if the soil wants to move a lot more than the pile, it has to go past the pile, right? So, as it tries to go past the pile, it says, oh, you are stiff and I want to go past you, so I will mobilize my passive pressure. The biggest problem with soil is whenever it wants to go and somebody is trying to stop it, it will mobilize a passive pressure, which is a lot bigger than a normal, say, earth pressure at rest. So, because of that, the pile will see extra loading, and that is what we call kinematic loading. So, it's that the hint, the clue is in the name. Kinematic loading is coming because something wants to move and somebody is stopping it. Inertial loading is coming because someone wants to move and the other fellow doesn't want to move. The building doesn't want to go, the piles want to go. Therefore, that is called inertial loading as defined by Newton all those years ago. Now, we have seen umpteen examples of these piles failing. Again, this is why it's important to go and look at these things that have fallen over. This is from Taiwan 921 Chichi earthquake, where you got this bridge, not big bridge, it's a fairly minor bridge with piers, and the whole of the pier rotated, making the decks fall off. You can see the decks have fallen off the pier. Why is that? This is because the decks are very heavy, and when the earthquake came, the decks wanted to slide back and forth, and in doing so, they pushed the pier and they broke the piles at the bottom, at the top of their head. Then the pier could rotate, which means that there is enough space for the deck to fall down. That's what has happened. So this is a case where inertial loading from the superstructure, the decks and the pier, applied large lateral loads on the top of the pile, failing the pile and therefore causing the failure. The other case is the kinematic loading. Again, same earthquake, different bridge. Here, as I said in the previous lecture, if I have sloping ground and the sloping ground liquefies, it will go for spreading, right? So, it will spread down, and these are the longitudinal cracks I showed you in the previous lecture. So, this is all because the soil wants to go towards the river, down slope. It doesn't particularly like when we put big bridge piers and piles in its way. So, what we have done here is we've created a large bridge pier in that slope, and the soil wanted to go down slope. You can see this, it moved away from here. This used to be here, it moved about 3/4 of a meter. And that is a bigger close-up of that. That is not a problem. Soil leaving the pier and walking down the slope is not a big issue for us. But equally, same amount of soil wanted to come from the top, right? Now, this pier is the one who's stopping the soil from coming. As I said, if the soil wants to leave the pier and go away, it will go with nice active pressure, which is less than earth pressure at rest. Ka is less than K0, right? So, that is not going to cause us any problem. But the one that is coming is going to come with Kp, which is 9 times larger than the active earth pressure, roughly. If you take phi as 30 degrees, it's 9 times bigger. So, the horizontal loads that your pier is going to see because of this will be huge. Even if I had 2 meters of soil, 2 times say 15, to keep the numbers simple, 15 kPa is 30 kPa. That's my vertical stress. Multiply that with a factor of 9. That is how much horizontal stress I'm going to get. And you integrate that over the area of the pier, the load will be significant. And that is all actually kinematic load coming onto the piers and the piles below because the soil wanted to go walking and you stopped it. It doesn't like that at all. So, this is all coming because of the movement of the soil. Therefore, we should call it the kinematic loading. Right. I'm not the first one to talk about inertial and kinematic loading. This has been going on for some time. And let's see where we are. Now, typically say I got a pile cap and say that is the column of the building and the cross beam or the ground beam. So this will sit on these normally. But what I want to say is that the structure will have its own acceleration, say going from right to left. Then the inertial load will come the other way, and that will be the direction in which the load is applied onto my pile cap. Just the free body diagram of that. If you do that, if the pile cap rotation is allowed, in other words, this can rotate like that, i.e. this connection is not rigid. So the column is there, but my pile cap can rotate. That means I'll form two hinges here. If my pile cap is not allowed to rotate because that is connected solidly to my pile cap, then it can't obviously rotate. So it will go translating and therefore it will bend like that. If I got a lot of depth here, I can accommodate that much movement without forming plastic hinges. But if these are shorter or smaller layers, then I will form plastic hinges. Okay? So that is clearly where I am trying to stop or have a particular type of failure in my piles depending on what the structure is doing. This so far we haven't got the soil involved at all. The pile cap is there, the piles are there, but depending on how the structure is connected to the pile cap, we can get different types of failure mechanisms. So this is one example of this soil structure interaction. We need to know what the structure is doing. Is that a framed building? Are there cross beams joining? All that detail we need to know before we can determine what the type of failure is. Now, because the buildings are quite heavy normally, your inertial loads are always going to be very big. What is kinematic load? In the other way to create kinematic load, suppose I got an earthquake, stiff clay, soft clay, my piles are going through the soft clay and into the stiff clay, and because of the shaking, let's say I got the displacement profile, it used to be vertical, I formed this kind of shape. So the piles want to do this and the soil wants to do this, and because these two displacements are not matching, I will get the kinematic load coming onto my piles. Again, the kinematic load may be more on the front pile compared to the back pile and all kinds of funny things. It also depends on the pile spacing, and there's a lot of research we have done and other people have done to see what is the load difference between front pile and the back pile, and so on. Again, if the pile cap rotation is not allowed, you will get a totally different failure mechanism. Another point is, this is quite important, is will the inertial load and the kinematic load will happen at the same time or not? And this is what we mean by phasing. So it is possible that the earthquake comes and it shakes. So at that time, I have my inertial loading. But the earthquake shaking causes the soil to go walking down the slope. That will happen maybe after the earthquake is finished or between at least some time after the earthquake has started, right? So the kinematic load and the inertial load may not be in phase. They may be out of phase. So you should not again simply take peak inertial load, peak kinematic load and add them together. That is probably too conservative because they may not happen at the same time. But if you want to be conservative, you can do just that. Right. The other thing is, how do you know whether the piles are rigid or flexible? So this is one way the Eurocode kind of tries to do this. I'm not a fan of this, but I can't only teach things I like. When the other people have done some things, even if I don't like, I have to at least mention them. So what they have done is, you need to know what is the active length of the pile. That's what LAD is. In other words, for example, in this case, although I have pile all the way going down, this bit of the piles are probably just straight. So they are not doing anything. So I only need to know this length of active length of the pile which is undergoing bending. And this is a way of calculating that. So what they say is you can calculate this by 2 times the diameter of the pile, ratio of the Young's modulus of pile to Young's modulus of soil at one diameter depth, one pile diameter depth, to the power of 0.22. Again, it's a fitting exercise. That's why they come up with that kind of stupid numbers. But more importantly, before I get too upset about 0.22, I got more upset with this EST. What is it? I've been in soil mechanics for nearly 40 years now. What is Young's modulus of soil? This is not steel, this is not concrete. Our soil doesn't have Young's modulus, let alone measure Young's modulus at one pile D below ground. One pile diameter, say it's half a meter diameter pile, you're looking for vertical stress half a meter below ground, which is tiny, and you're trying to say, oh, I want to know the Young's modulus. There is no such thing. So this is a stupid thing that numerical people have. In computer code, you can enter a number, and okay, we put Young's modulus for soil, for steel, Young's modulus, Poisson's ratio for steel, concrete, likewise. Why can't you guys do the same for soil? And that's because our soil doesn't behave that way. But anyhow, this is what is in Eurocode, and that's what it is. Then the pile flexibility they calculate as, say, some factor T. Again, Young's modulus of pile, fine. So EI of the pile, and here K is the subgrade reaction. Again, this is like measuring the spring stiffness of soil, and this, and you can see why this is stupid, right? K can have values from 200 to 2000. Really? That is a factor of 10 on design? Yes, we can put the numbers. We can do, if it is an exam question, students, you give the number, they'll put the number, do the it's just an calculator exercise. It doesn't mean you're doing any design. Anyhow, so if it is loose soil, they immediately plug the higher end of that number, 2000. Don't ask me why. Similarly, for inertial loading also, you can work out the elastic length Z max based on L over T. So I already got my factor T from here, and I know the length of the pile. So Z max is the active length of the pile, or LAD. Okay. So if it is greater than 5, the pile is flexible. If it is less than 2.5, the pile is rigid, and in between it is semi-flexible. Similarly, methods are also there in Brom's and other textbooks where you can see whether the pile is flexible or rigid. But this is for more dynamic loads. So what about inertial loads? So that bit we looked at pile movement and soil movement and where the length of the active length of the pile. But when it comes to inertial loading, it is again we need to determine whether the pile is flexible or not. If it is flexible, it will move with the surrounding soil, and therefore it will attract that inertial shear load at the top of the pile head, but the kinematic loading will be small because the pile is already moving with the soil. There is no, it will deform the same way as the soil does. So the amount of kinematic loading will be small, but you pay the price in inertial loading. Rigid piles, on the other hand, will stay there where they are. So hopefully you will get less amount of inertial loading, but more amount of kinematic loading. So how do we work these out? So you work out the kinematic interaction factor is defined as this IU. Basically, what is the pile displacement any depth divided by what is the soil displacement. So we are dividing the pile displacement with soil displacement to get my interaction factor, IU. And then we can also work out this dimensionless factor F, which is, here is the first bit of taste of dynamics coming in. F over Fn is the frequency ratio. So F is the earthquake predominant frequency, Fn is the natural frequency of my pile soil system. So that is the dynamic bit. This is the stiffness bit, EP over ESD, pile Young's modulus over soil's Young's modulus to the power of 0.3, and L over D is just a geometric factor, length of the pile over diameter with minus 0.5. So if I have this F, I can link that to this IU through these, and basically Eurocode gives these ABC values for clearly a fourth order polynomial somebody fitted to this. Okay, and depending on how the soil stiffness is changing with depth, if it is constant, you have these values. If they are parabolically changing with depth or linearly changing, these ABC factors change. So you plug these into there, work out the IU for kinematic interaction. Okay, now this is all great. So we got a recipe for working out kinematic interaction factors and inertial interaction factors, right? Are they any good? Mostly I'm focusing on inertia, kinematic interaction, because inertial interaction, I can always take the mass of the building, multiply that with the earthquake coefficient, and I can get the, sorry, it's auto-playing. Multiply with the PGA, I should get the total possible inertial load. It can't be worse than that. And I can divide by number of piles. I'll always get that quite easy. Kinematic interaction is more important because that depends on what the soil is doing as well. So this is work Tejesh has done. Garala is a new assistant professor at IIT Madras. And when he started, came to look at soft soils, piles in soft soils. So all kinds of soft soils can amplify the seismic motion, and they're influenced by amplitude, frequency, and duration of the ground motion. That's what we want to look at. And there are plenty of examples where soft soils caused trouble in the past. This is the Mexico City 1985 earthquake, where the earthquake was fairly small away on the hills, but at these locations it has magnified from 0.05 G to almost 0.2 G, and that caused all these buildings to fail, and buildings of certain height to fail. Very tall buildings were fine, very short buildings were fine. The buildings which were 20 stories to 25 stories all collapsed. And this was a very interesting problem to look at that time. And people did work like, how the depth of the clay layer increased from here to here. It goes deeper and deeper because Mexico City is on a clay bed, a dried out clay bed, so the clay is very soft. It's a very famous geotechnical case. So what we did was, we had piles which are short in soft clay. So his system was soft clay then sand. So we had single pile group of 3x1 pile group, all stopping in clay. And he also had in another experiments, the piles went into the sand. So we'll start with the clay ones first. And that came so this is the experiment. Again, I'll do the centrifuge modeling part tomorrow. I can't do everything at the same time. But you can see he created a soft clay and he installed these piles, and everything is in clay. So these are what you would call floating piles. So piles which are not actually going into the sand. And he tried different earthquakes. I'm not going to go into all the detail, but we can also push this like CPT. We can also do a T-bar. So while the centrifuge is spinning, we can push this T-bar, which basically gives us the, like QC, you can get it's linked to underhand shear strength. So we can measure underhand shear strength with depth while the thing is going on, before the earthquake, after the earthquake, and so on. And we can also measure shear wave velocity using another device called air hammer. You shake this air hammer very gently and pick up the upward propagating waves, and you measure the shear wave velocity. based on wave arrival times. So this is all done, and again there's a paper if you want to look at that. But the interesting thing was that we could see how the accelerations as they go through the clay change. So there are some components which get bigger and some components which get smaller. By the way, this work was done with the SAM actuator, so we didn't have the servo hydraulic actuator right then. He used it later on. And what we could see is that for bigger earthquakes, these high frequency components are disappearing. So clay is acting as a nice filter to get rid of high frequency components which are there at the bottom but not at the top of the clay. Also, we could work out the using this G over G naught curves where our data falls and fit a line through that and work out at any depth what the shear stress is. It's just a bit of maths, don't worry too much. But what we worked out is, if I look at a certain depth like this, beyond above here, my clay is not strong enough to carry the applied earthquake. So I'm applying here an earthquake that is nearly 0.25 G. Okay, very strong shaking. So if I apply very strong shaking, clay does not carry this above because its shear strength is only that there. If I exceed the shear stress, it is not going to carry that above that elevation. Okay, so it basically it fails nicely there and protects your structure on the top. So we want to kind of use this to make holes in deep soil. Deep soil is a computer code which people use routinely to do site characterization. So if you put the same, so if I put small earthquake, everything goes through. Big earthquake, our experiment is showing the accelerations all fall off, right? But if you do the deep soil analysis, which doesn't have a failure criteria built into it, it will predict, because the soil is like a clay, a soft sponge. If you shake it strongly, it says it wobbles a lot. And so you need to have some yield criteria in the program, otherwise it will predict. So the blue line is what the computer prediction is and black line is the reality. So you should not use computer codes without knowing what they are doing. And the pile response also you can see, if I apply the big earthquake, although the clay doesn't respond, the top of the piles actually oscillate a lot. That's because I use the pile to connect the stiff part of the clay to the top. So the rest of the clay gets protection because it gets isolated, but the pile itself will carry the load and oscillate quite strongly. Okay, that's all fine. The other part we did was to put these piles into sand. This is the most common case. Floating piles are very rare, to be honest. So that was just fun and to tease the guy who wrote Deep Soil, who I know, Hush Hush. Yosef Hush Hush was the guy's name. Anyhow, so we put single pile and multiple group piles into this profile. Come on, yeah. And again, we can measure the strength with depth, undrained shear strength using the T-bar. We also do the shear modulus, and you can see this is where the jump in stiffness happens, because this is all sand, that is all clay. This one is only being plotted up to here. Okay, this 6 meters or 7 meters ends here. We can't use our T-bar to be pushed into sand, otherwise it will break. Sand stiffness is 100 times bigger than clay. So you can either design the device to work in clay or sand. You can't do both. So that's why you haven't got CU profile in sand, which doesn't make any sense. Anyhow, we got the natural frequency of this, and most importantly, we measured the bending moment of in the pile. for different earthquakes, right? We got these are the points where we are measuring the bending moments, and now we've done that, we could compare the minimum and maximum bending moment envelopes. And luckily for us, in literature, there are quite famous people who put their name and gave estimations of how to calculate kinematic loads on piles. For example, Ricardo Dobry, Tom O'Rourke, Nicolaou, Milanakis, lots of big names. And all Tejesh has done is to collect all their equations, and he worked out these values according to what they said, and he plotted the maximum bending moment that we should get based on their calculations. So for small earthquake, blue line is our experimental one. Those equations always give you the number at only one depth. You can't do them for different depths. So he chose this 9 meters is where they calculated. So we also did the same. And this is where the experimental values are. This is value is, and these are all the predictions for by different researchers. So great, no problem. That is not too bad. I mean, for small earthquakes, it works fine. But when we increase the size of the earthquake, the peak bending moment for us goes up to about 450 kilonewton meters for this sized pile, and all the theoretical predictions fall here. So, oh, that is not good. That means all these equations that are there can only work for small earthquakes. If the earthquake size is big, we are in big trouble because we are getting a factor of 2, 2.5 above what they're estimating. And as I said, our factor of safety for pile design is about 2 and 2.5. So all of them will fail. So we wrote a paper to compare the bending moments with the theoretical predictions. Our centrifuge data is showing all these black dots, and you can see all the theoretical ones are tailing off here. So we are getting, for bigger earthquakes, we are seriously underestimating what the peak kinematic bending moment is in the piles. So what have we learned? So we have learned that pile foundations have this type of loading called kinematic and inertial loading. Those are separate. And there are ways, theoretical, semi-empirical, some made up methods for estimating the inertial and kinematic interactions between the pile and the soil. We've seen those. But more importantly, we learned that if you design the experiments, you can get at least validation or otherwise of how good these solutions are. And I hope I have shown you that if just by considering bending moments, nothing else, we could show that the existing methods work reasonably well for small earthquakes, but fail miserably when it comes to large earthquakes. So the process of learning was there is this problem of pile foundations. There is static load, dynamic load. There is ways of calculating them, but more importantly, we must have ways of telling the calculation procedures are right, overestimate, underestimate, is it safe or not. Okay, so I'm going to stop there. Any questions? No need to. If you clap every time, we'll be clapping. You can clap at the end of the course. Okay. Yeah, yeah.
Normally in end bearing estimation there is CPT, there is an averaging of 2 diameters up and down.
Yeah, yeah.
Why it was not?
You could do. I mean, here you can see because it's coming at the. This is coming quite low. So whether you average it up and down, it's not going to make difference. I'm not. There are many variations of applying the CPT. I'm not arguing one is right or not. Also, the CPT at very shallow depth, the failure mechanism doesn't fully form. Therefore, it is also there. I think Dave White or somebody came. There's a paper saying how do you correct for shallow layer correction for CPT and T-bar values, especially for soft clays. offshore Perth, right? Yes, you can do that. I'm just trying to teach that try to use CPT direct correlation. I like that because you're doing exactly the same thing to the soil, whether you're driving in a pile or a CPT. So surely we should be able to scale from CPT to pile much better than trying to work these bearing capacity factors randomly. For offshore, you certainly should use CPT, no question.
Of course, again, another question is related to this. Since we are pushing CPT T Preston itself is an average value.
It is what it is, right? It's what soil is doing.
It is a like average value. And again, why we are doing this averaging?
Oh, that is because of the layer. Yeah, CPT is a funny thing, right? We have some very interesting experimental results. When do you think the soil will feel the arrival? Say I'm driving the CPT here and I'm the soil here. When do you think I'll see that CPT is coming? Can you guess? So the CPT can be felt by the soil element maybe 3, 4 pile diameters ahead. So when the CPT is here, I can already feel the increase in stress. Then it goes increasing until it goes past the location, and then once I go past, you can see that it starts to relax. So you can pick this up using the pore pressure transducers around, and there are very beautifully done experiments. I think Delft or even Nantes has some tests like that to show the arrival of the CPT. So yeah, that is why they try to average the along. That is to account for the length direction along the driving direction. This what you are saying is along the lateral direction. So you need both. It's but the good thing is if it is doing that for the CPT, it will do the same when you drive the pile. That is the assumption, right? It's just a scaled up version of that. Any other question? Uh, Professor, you would ask something? No? Okay. Right.